Good morning, good afternoon. Hello, Hamza.
Hello, Quentin. Hello, everyone.
We are very happy, Hamza and I, to present you what we are doing in the field of AI-driven retrosynthesis. And maybe before starting, a few words about Iktos. We are a small startup based in Paris, incorporated late 2016. We are currently 30 people working in the field of artificial intelligence applied to chemistry. Two main fields. The first one is generative models for de novo drug design, and the second one is data-driven retrosynthesis, which is a topic of today. We work with different type of business models, services, research collaboration, and also software, Makia for de novo design and Spaya for retrosynthesis. Okay, so the concept of retrosynthesis has been announced by E.G. Corey, who has been awarded by a Nobel Prize in early 90s. The concept is actually quite simple. You have an input molecules you want to perform the synthesis, so you have to think in the reverse way by recursive deconstruction of this target compound through a series of chemical feasible reaction steps. Okay, let's say we want to retrosynthesize ranolazine, which is here the input molecules. We have to think what can be the last reaction. So the first retrosynthesis step, and recursively we will try to think about that at each step until we end up to commercially available starting material. Then if each steps looks reasonable, you can go to the lab, buy those compounds and perform the synthesis. So maybe Hamza, can you explain us the concept of the tree search and what do we have behind all this type of possible disconnection? Because actually we can imagine that we can perform a lot of type of disconnection. And
Yes, as you say, if you want to think together to a simple algorithm in order to perform retrosynthesis analysis, maybe the first thing we should think of is having some component that performs disconnection, that take products and transform it to its precursors or the reactants that can give the products. So imagine that we have such a component. If we use it over and over on the molecules we have, we're going to have many routes that either will end up to commercial compounds or will end without finding solutions given some accepted lengths of synthesis routes. Here, these components can give us many possibilities of disconnections. So when we think of using it over and over to make the disconnections, we can easily see that we have a tree structure that can grow in an exponential way. So having said that, this is the main idea of any algorithm that's the basic idea of any algorithm that's performed retrosynthesis analysis. But such an algorithm is naive, and the first question we can ask ourselves is how can we make it more intelligent? How can we save time and perform a more intelligent search in such a tree? So that's the first question we're gonna try to give an answer to with Quentin. Another question is that reactions maybe are not all feasible. So we should have some we should be able to assess the feasibility of reactions. So that's also another major topic in retrosynthesis analysis. And maybe the third one is how such a component that we assume we have to make the disconnections, how can we make it, and how can we do it using in a data-driven way? Quentin.
yeah, so actually this kind of search through this big tree of possibilities, during many years we thought that it was too complex to accomplish, but actually, two main example have been published, and those type of challenges has been overcome either in the case of Deep Blue or in the case of AlphaGo. We during many years thought that this kind of game were only for human, but artificial intelligence have demonstrated that actually it is possible. But it doesn't come overnight. It took many years of mathematics and informatics to achieve such impressive goal. It's the same in chemistry, actually. During many years, and even Ejikore tried to develop softwares to perform retrosynthetic analysis, but during that time, mathematics, informatics was not at the level of today. And now we arrive at a certain level which bring enough performance and to be able to start building some tools which start to actually produce impressive results, and now the community consider using this type of technology to help chemists in their everyday life. So there are two main approaches to extract knowledge, actually. You have the first way, which is expert-based system, where the rules are extracted by human chemoinformatics chemists try to understand the context of the chemistry. And you have another way, which was more recent, actually, which is data-driven approach, which automatically extract this knowledge from the databases. Today we will focus on the second one, the data-driven one, because Spaya is purely data-driven approach. But before going through the algorithm and what there is under the hood of Spaya, I think it's very important to understand what can we expect from those technology and actually what a chemist wants to see with such softwares. So first, user experience is something very important. The chemist wants a very easy interface. He wants to have access to the literatures, reference very easy, to have trust into the disconnection, but he wants to be able to influence the search by be able to limit the price of the starting material, play on the number of steps, but also which bond I want to break, which intermediate I want to pass by, etc., etc. But also, he wants that the tree ends up to a commercially available starting material, which is obvious, but actually which is not the case of all the softwares. Regarding the technology implementation, which is also very important, because for a chemist it's very important to be able to take advantage of his proprietary reaction, but also its in-house database of commercial compounds. Also chemoinformaticians who are less sensitive to user interface, but in their case they want an API to be able to connect this technology to virtual library, generative models. Also, time response and scalability is something very important when you want to score thousands or millions of molecules. And under the hood, chemists are expecting technology which are able to handle radioselectivity, chemoselectivity, protecting group strategies. Also, chirality, and which is also something important, is to be able to score the routes, to have first position best routes. So to perform and to build such algorithms, such technologies, you need three main pieces. The first one is database. So you need a database of reactions to extract the knowledge of chemistry. You need commercially available starting material or intermediates, to stop the retrosynthetic analysis. And also you need, of course, an algorithm which is which needs how to predict the disconnection, which needs to detect if the reaction is going to be feasible, and of course it needs a search strategy to explore the tree of disconnection, and finally an interface, of course, to play with such technology. Hamza, can you explain us maybe how to predict a disconnection?
Yes. So here to perform this connection, we use a supervised machine learning model that takes as an input a molecule and then tries to predict the most probable reactants that such a molecule can come from. Those type of models can be split into two categories. The first one, which is the template-based models category, it uses templates. When I say template, it's a rule of chemistry. It predicts a template, it predicts a rule of chemistry, and then apply it, and then we can get the reactants. We can get the most probable reactants, which is how the disconnection can be applied to that molecule. The second category is what we call template-free models. For these models, there is no need of having such chemistry rules. We try to predict the reactants directly from the input molecule. In Spaya, we use today template-based models, and that's this type of model today is running in production. So I talked about a template. Here is an example. So as we see, a template is for a reaction what a regular expression is for a sentence. So basically it matches a pattern in the reaction, and when it's compatible, it can be applied and give us the reactants. So here we have an example of a template compatible with the reaction, which is a ranolazine, and we can see an example of reactants given by the disconnection. Quentin.
So how can we extract those templates actually? So first, as we said, we need a database of reaction, which can come from providers, public database, for instance, US patent database, or also your ELN actually. And in those databases, you will find, as you can see, reaction smiles. So smiles is a common representation of the molecules in its string. And as you can see here, you have this reaction here represented by this reaction smiles. So this is actually the raw data we use to extract templates. So let's say you have this kind of reaction, which is nitrile reduction. You can see sometimes you can see that you have hydrogen, palladium, ethanol. Sometimes the solvent is present in the reagent part of this reaction. Sometimes it's in the product. Sometimes, as you can see in this example, reagent and product. So we can have sometimes very dirty reactions, and so you have to clean that, because if you perform directly the atom mapping on the raw reaction, you may end up with a lot of mistakes. So first you have to clean this reaction, remove some solvents, remove some spectator reagents, intermediates, etc. So you perform this reaction cleaning, and you end up with the reactants and the products, and once you know the reaction is clean, you perform what is called atom mapping. Atom mapping is a way to identify atom on the reactants and the same atom actually on the products, so that you are able to see which has been removed, added during the reaction. And here we can see that between the carbon 2, nitrogen 11, the triple bond becomes single bond. So it's very easy to extract this information and to put it in the reverse way, so in the retro and you build a retro template saying that this primary amine is coming from this nitro. So you do that on the full database, and at Iktos we are working on the database provided by Nextmove software, which is called Pistachio database, which contains around 10 million reactions automatically extracted from US patent database, but also European database. After the reaction cleaning, as we explained just before, we remove also duplicates, solvent removal, etc. So we end up to 3.5 million reaction. You perform the atom mapping, you extract the templates, so you have a clean database of 2.8 million reaction. Almost 80% of the database has been properly extracted, which is actually a very high number because atom mapping is a complex steps in this process. At Iktos, all this process has been is fully automatic, and in less than a week we are able to perform this full data preparation. So how can we predict those templates actually? Maybe Hamza, you can explain us which type of models and technology we can use to predict which template to apply.
Yes, so now that we have a database that is cleaned and that we have managed to extract templates from reactants, we end up with tuples of reactant templates, which make a clean data set for training a supervised learning algorithm. So here, as we can see at the left, we have three reactions that are linked to the same rule ID X, which can be regarded as a class when we consider the problem as a multi-class classification problem. So here it's the nitrile reduction, and we can see another type of template, which is the retro ID Y. That's basically an esterification. So the goal here is to, for each product, take the product, transform it to a fingerprint or some representation, give it to a neural network, and try to predict the templates that are the most probable to be applied to that product. So as we can see next, the architecture we used to tackle that problem is a simple feed-forward neural network, starting from the Morgan fingerprint, which is a famous fingerprint that we use in our daily life in chemistry, in chemoinformatics, and that ends up predicting probabilities of the templates. So if we can give you some statistics of the training data sets, we have, as we saw, we have 2 million reactions, and to those reactions we can associate 62,000 templates. So as you can see, the high number of templates and the fact that some templates can be represented by few reactions, those are factors that made the problem not so easy. As we can see, we have a top 50 accuracy of 95%, which means that when we have a product, we have 95% chance of getting the right disconnection when using our model. So here, the model catches the pattern from the training data sets, but as any learning algorithm, the real goal is to generalize and to be applied to new molecules that are maybe new or not present available in the training data set. And this is actually the magic components I talked about in the introduction. So if we have that, we can perform these connections and we can apply over and over to get the precursors in a recursive manner. Quentin.
Okay, so now we have a disconnection prediction. We have to make sure that once we have applied this disconnection, actually the reaction is feasible. So let's say we've we apply these templates, which is actually the top one prediction by disconnection predictors. These templates appear at the top one position. If I apply this template to ranolazine, I end up to those starting material actually. As you can see, carbon, nitrogen, and oxygen somewhere become carbon, oxygen plus nitrogen somewhere. So actually, this is what happened here. You have carbon, nitrogen, oxygen, and now the carbon is linked to the oxygen, and the nitrogen appear to be alone as in these templates. So this looks good actually for a chemist point of view, but as you can see, you have carbon, nitrogen at different places of this molecule. So if you apply these templates on the ranolazine, you end up to that, but also to all this kind of crazy disconnection. And if if you go to the lab and you mix this plus this, you won't be able to obtain that. So you have to get rid of this kind of crazy disconnection. But also, you can have some radioselectivity issue. For instance, you want to perform the retrosynthesis of this indole carbaldehyde. We can think about having the retro rule 94, as you can see, which appear in the 10th position. So the aldehyde, to obtain this aldehyde, you perform kind of a free L-craft reactions. And but actually, if you go to the lab, you can have this reaction which can occur in different position of this indole. So you have to be able to tell to your algorithm that retro rule 94 is not a good idea, and you will have issue of radioselectivity. So for that, you have to find a way to get rid of this this reaction. Maybe Hamza, you want to explain which type of technology we can apply to get rid of those type of reactions?
Yeah, so in the literature, many ideas have emerged to tackle that problem of feasibility. Here we can have the first ideas to build a classifier that takes the whole reaction and that tells you if it's feasible or not, if it's true or not, if it's close to some reaction in the literature or not. So that's the principle of this type of classifiers. The second approach is to take reactants and do a template-free translation based on text or on graphs. Different technologies can be proposed for this for such a purpose, and to translate it to the product. So here in the second approach, we after making the disconnection, we view on the reactant side and see if the product is, if actually we can predict the same product that we just split into the reactants. So both approaches can be applied with some advantages and drawbacks. We at Iktos have developed a proprietary system that split the problem of feasibility reactions into two distinct problems. The first one is what we call applicability domain estimation. It means that if I have a template, a reaction, and a literature, and can I estimate if applying this template to this product is among the applicability domains of what I know in the literature. So that's the first part, and it's enable us to allow us to filter crazy disconnections that Quentin showed you some examples of. The second part is a radioselectivity filter, which focuses on explicitly on the problem of radioselectivity and selects the right radioselectivity according to its knowledge. So stacking both filters, we end up with the Iktos filter, and Quentin will show you some examples of applying that filter.
Yeah, so For instance, on the ranolazine example, if we applied our applicability domain estimator, we can see that, and this is a screenshot of internal application we have developed at Iktos to be able to debug Spaya and better understand how the system is working. And you can see that here, this is valid for our applicability domain estimator, which is not the case of those kind of crazy disconnection. Regarding the radioselectivity filter, you can see that in the forward direction, this free aircraft reaction has been rejected by our radioselectivity filter because we have a probability of 0.48. So what about chemoselectivity, which is another difficulty actually you have to tackle, for instance, and we believe that this is one of the biggest issue actually. For instance, you want to synthesize this acid moiety, sorry, you can think of the algorithm can think of this retro rule, which is condensation of Grignard to this bromo derivative. But we all know that a Grignard can be quenched by this acid moiety and maybe won't be able to react with this bromo derivative. But actually we know that if I put two equivalent of Grignard, the reaction will work actually. So this task of taking those two reagents and to be able to predict the output of this reaction is something which is highly complex, because with one equivalent of Grignard, the output of this reaction will be this starting material actually, but with two equivalent of Grignard, the output of this reaction will be that product. So this is something quite complex actually. Today, you know, the best method described so far has been described by Alfali, and where he showed that using molecular transformers, you can reach a 90% accuracy for the top one prediction, which looks very high actually. But this, you can reach such level of quality of prediction if you have at least two reactants. But it's not the case in real life actually, because if you go to Pistachio database after cleaning and template extraction, you have more or less half of the database which contains actually only one reactant reaction, A gives C. And in that case, molecular transformer performance dropped to 66% accuracy for the top one prediction, which is actually not enough to use it in production. Moreover, to those molecular transformer, they appear to be quite slow, even on GPU, and using GPU in complex infrastructures is something not easy and also very expensive. So that limits the implementation of such technology. So how can we handle chemoselectivity? Actually, we have been able to observe that being able to predict accurately the disconnection is something very valuable. For instance, if I want to make that compound here, the algorithm proposed us to condense this Grignard to that ideal aldehyde derivatives. And we all know that Grignard can react on aldehyde, ketone, or esters. And so why the algorithm propose this reaction? Because we can easily imagine that we can have some problem of chemoselectivity in this reaction. But actually, if you go to the literatures and you see the most similar reaction, you can see that the algorithm has been inspired by this reaction. And as you can see in this reaction published in the literature, you can see that is it possible to condense a Grignard on the molecules which contain an aldehyde and an ester moiety if you use one equivalent of Grignard. And here we have one equivalent of Grignard and one equivalent of this 4-mil cyclohexane carboxylate. So actually, if you have very good predictor of disconnection, by seeing that project, the algorithm is able to understand the full context of these molecules and to propose a reasonable disconnection, even though you can have some different reactive centers. which is actually very similar to the notion of protection, deprotection strategies. For instance, if you want to synthesize that compounds, the first rules which is proposed by the disconnection predictors, actually, as you can see, is an acetal protecting group with a very high probability. So by seeing that molecule, the algorithm is able to see that if you want to do chemistry on that compound, first you have to start by a protection group. So again, we observed by experience that having a very good disconnection predictors allow to get rid of most of the chemoselectivity issue and also strategy of protection deprotection. It's not perfect, but it allows you to in most of the case to be able to propose reasonable routes. Also at Iktos, we believe on the community enrichments. And in cases you encounter in our softwares some crazy disconnection, or maybe you spot some issue of chemoselectivity, we allow the user to like or dislike some reactions. And this information is very valuable for us, which allows you to improve the quality of the output of the softwares. Also, once you have built your own tree, you are able to save the roots, and we assume that if you are happy with that roots, it means that all the steps looks reasonable, and this is also for us a very important information. So we talk about disconnection prediction, reaction feasibility. So now we need an algorithm to explore the full possibilities of disconnection prediction in this big tree. So Hamza, can you explain us what is the theory behind this search strategy?
Yes, let's make the exact research and exact exploration more intelligent through reinforcement learning, actually. So just let's explain let's make a reminder of what is reinforcement learning through the Pac-Man video game example. So in reinforcement learning, we have an agent interacting with an environment. So here the agent is the Pac-Man player, and the environment is the maze, the gods, the dots, and all the environments of the game. And the agents can take some actions, can choose which directions to go. So that's he takes an action. Environments give him a reward. So if you eat a dot, you are given a high reward. If you're eaten by a ghost, it's game over. If you eat a flashing point, then you can eat a ghost and get even higher reward. So based on those rewards, you try to adjust your state by taking another action. And here the interaction goes between the agents and the environment. We talk about policy in reinforcement learning. It's just a function or some way that determines the behavior of the agents. So it tells him which actions to take given a state. We talk also about a model in reinforcement learning, model-based reinforcement learning. A model is just a way that tells you, that models the probability of being at some state given your state and the action that you took. So basically here, the model can be some neural network that captures the maze and tells you the probability to go right or go left based on the image of the game. And of course, the goal of reinforcement learning is to find the optimal policy. And an optimal policy is a policy that maximizes cumulative reward. So here in Pac-Man, the goal is to win the game with maximum of bonus. And again, retrosynthesis can be also formalized as a reinforcement learning algorithm. So maybe the environment is chemistry of reactions. The agent is trying to find the best routes that retrosynthesize a problem, and reward can maybe link to the fact that that to be to be split into commercial compounds. So in reinforcement learning, we have a formalism which is called MDP, and Markov decision process. So it's a formalism that allows us to solve the reinforcement learning problem. So here in the case of retrosynthesis, the states can be imagined as a set of molecules. An action can be taking an action is to split some molecule of the set, and the reward is proportional to how many molecules in the set are commercials. And policies can be viewed as a path in its research. Maybe in the disconnection, in the exact research that we saw, following a path in that tree is a policy. And the model can be considered as the disconnection network, which gives us the probability of making some disconnection given a state which is a molecule and action taken in the past. So the solution for this Markov decision process for retrosynthesis is Monte Carlo tree search. What's the difference? What's the difference between Monte Carlo tree search and the exact tree search? So basically, Monte Carlo tree search performs a growing of the tree in a manner that makes a trade-off between exploitation and exploration. So it goes in a vertical way in the nodes that are the most promising, and then tries to explore some other propositions to have some diversity in the solution that we make. So in a Monte Carlo tree search, we repeat within a time budget. I say time budget is just number of iterations of that we can have 4 steps. So the first step is selection. It's basically going through the tree and choosing which leaf to be in at that step of the algorithm of the run, and it's in this state that we perform the trade-off between exploration and exploitation. So maybe if a node is really promising and we've seen it a little bit, so maybe we should exploit it. And if we visit that node many times, maybe we should go to another node and maybe explore it to have some diversity. The second step is expansion. In expansion, it's here when the growing of the tree occurs. So here we use the disconnection network we talked about to create children. And we also use the filters to remove crazy disconnections and to remove bad regional selectivity. In the third step, which is simulation, we apply our disconnection network in a recursive way until we reach a terminal state, which is either a state that contains commercial compounds, or until we reach the maximum depth of the tree, and then we stop. And doing this allow us to assess the quality of the node, to check if this node is promising, and if we should select it in the next run. And at the end, the last step is backpropagation, which is updating the parents of the node that has been simulated, and updating with the reward that we've just seen, in order to update their quality score. So those are the 4 steps of a Monte Carlo tree search. So that's fine. Monte Carlo tree search is a cool algorithm that makes the exploration of all the possibilities more intelligent. Here at Iktos, we have an implementation of a Monte Carlo tree search that is strongly coupled with a database storage. So which means that we have a Monte Carlo tree search that has some memory in the current run, memory of the past runs, which is for the future runs. So the tree search, when we have a run, when we perform retrosynthesis analysis of some molecule, the tree search stores its results in database. So Spaya gathers chemistry knowledge over the runs, and it uses this memory during the most important parts of the Monte Carlo tree search, which are expansion and simulation. So if I have some expansion in database or some simulation results in database, I can use them and not use the models. And the third part is that the research is empowered by past retrosynthesis runs. So Spaya's research strategy, Spaya's MCTS improves over time, at least in a research points of view. So those are some benefits of having a Monte Carlo tree search with memory, and which means that a retrosynthesis that is not solved today can work in the future if there are some intermediate compounds that can make the search easier and that are stored in that DB storage, which can be used by the Monte Carlo research in the future run. Quentin.
So now we need to once we have performed this disconnection, tree search, and everything, we have to display properly the results, which is very important for the chemist. So first, at Iktos, we thought about having a good ranking to be able, like when you perform Google search, to have in first position best disconnection, best routes. So for that, we have computed a score which takes probability of the models and their applicability domain, so kind of the confidence. Also the number of steps. The shorter the route is, the better it is, of course, because chemists like short routes, elegant routes. And also something which is very important is this score takes into account the fact that the commercially available starting material are smaller pieces than the input molecules. So we would prefer a route which breaks, for instance, the ranolase in small pieces compared to a route which end up to a commercially available protected ranolase, for instance. And to put in first position the exact literature match, we have imposed a score of 1 if the algorithm is able to retrieve a route where it has been trained on. Also, something which we believe is a nice options is to be able to cluster the routes by the first retrosynthesis disconnection or the final reaction in the forward direction in order to allow which strategies to follow depending on what the chemists want to introduce on the molecules as a final step. For instance, you want on ranolazine to introduce diversity on the left part of the molecules. You would prefer these strategies in order to introduce diversity in this position. But if you want to introduce diversity in that compound in that position, for instance, in a medchem project, you would prefer this strategy here to perform the retrosynthetic analysis of that compound or the derivatives you want to produce. So we believe that clustering also is a very nice option to display the results. So what do we have today? What we will have tomorrow? I think it's interesting also to go through our roadmap. Currently, you have to copy paste the SMICE onto the interface. I will show you just afterwards, but the Sketcher integration is in progress. So maybe in 2 weeks from now, we will be able to you will be able to draw molecules Also, we are intensively working on the advanced search to be able to put some intermediates to limit the research regarding the price of the starting materials, the number of steps. We believe those options are very important in the frame of lead optimization project where you have synthesized, let's say, 100 grams of a given intermediate. So you want to take advantage of that. You don't want to have some routes which does not pass by this intermediate. So this is something which will be able to perform in Spaya very soon. Also, we are working on the batch retrosynthesis. Let's say you have 50 compounds, you want to perform the retrosynthesis. They are all coming from the same chemical series. You don't want to find a route for each compound. You want to find a common route to synthesize all these big batch, and if possible to have diversification in the last step of chemistry. So this is something we are also working on it. We are working also on the API development to be able to branch this technology to generative models or to perform big batch of retrosynthetic analysis. Reaction condition prediction is something very important. We are working also on it, chirality as well, and also how to improve the user experience, how to navigate smoothly through all the possibilities proposed by Spaya. So you will see that Spaya right now is in beta. It's free of access, unlimited number of queries. You can play with it without any limitation, and you have access to all the features, which won't be the case in the futures for the V1, where we want to keep some part of the technology free, because I think it's something valuable for the community, but you will have to pay for some options and to access to all the features. If you are interested to implement this technology on your infrastructures, please contact us if you want to have access to Spaya, the paid version. As we said, Spaya implementation is something, to be able to implement this technology easily is something very important. Currently, Spaya is deployed on our private AWS cloud. Is highly scalable. We can run hundreds of retrosynthesis in parallel, and of course, Spaya can be easily deployed in your private cloud, and which actually allow to even bring Spaya to a next level, because in that case you can take advantage of your in-house starting material. There is no need to perform a complete retrosynthesis if actually you have advanced intermediates in your fridge on your shelf. So this is something also very important for you guys to implement this technology in-house. But also we can also take advantage of your ELN reaction, internal synthetic knowledge. So to wrap up, our technology, so our AI technology, our pipeline of data preparation, plus your starting material, your reaction in your cloud, we can build a custom retrosynthesis softwares in less than a week, taking advantage of your chemistry and your knowledge, your intermediates. So I will now show you how to access to Spaya. I will perform a short demo. So very easy to access to the platform. You just have to go Spaya on Google. You will see some Thai massage, but most importantly for today, you will see that Spaya arrive in first position. So you just have to click on it. You arrive to the platform. You can see how it works on the FAQ. Also contact us if you have questions, if you want to report feedback. Most importantly, you can log in and register here. First name, last name, email, password, and in a minute you are logged to the platform. Once you arrive on the platform, you have a search bar. As you can see, it's a place to pass the smiles. back to our example, ranolazine, you can go to Wikipedia, have access to the SMICE, copy paste into Spaya. As I said, very soon you will be able to draw the molecules into a sketcher. Then we launched the ranolazine retrosynthesis. As you can see, it's quite fast. This is a simple molecule. The results, as we explained, are rank thanks to our score. The higher the better. Score equal 1 is exact match to the literatures. As you can see, we have some clusters which highlight the first retro disconnections. Then you can enter into the cluster. Results are each roots are displayed by the starting materials, and you can of course click on it and see the tree which is proposed. You can click on reaction, see the most similar reactions extracted from the literatures. Similarity equal 1 tells you that this is actually what has been published around the ranolazine, the first step of disconnection. You can of course see some similar reaction which has inspired Spaya to perform this disconnection. Sometimes you have the procedures, the time, also the yield, but also you can have access to the patent by clicking on the link. If you click on the product, you can see its price, if it's stock or not. Currently, we are working with MQL. We will soon integrate e-molecules and enamine starting materials. If a compound is not commercially available or out of stock, if you want to see how to produce this compound again, very similar way, you just have to click on more route from here, and the algorithm will try to find some ways to prepare that compounds. Again, clusters, ranking. So you have, for instance, here score 1 exact literature match. So you can build a tree with by yourself until you end up with reasonable disconnection, reasonable price of starting material, and then you can of course save your roots. So it's very easy to play with. Again, if you are not happy by roots, by a disconnection, you can you can like or dislike. This is really up to you, but you can also click on change and trying to find another way to produce that compound. For instance, this reaction, new price, new availability, etc. When you're happy with your tree, of course, you can save it. So please feel free to try Spaya. As we said, is freely available on the web. Feel free also to contact us, provide us your feedback. What do you think about the platform? What you want to see in Spaya? This is very valuable for us. Thank you very much for your kind attention, and please feel free to ask questions now. Thank you very much again.